All right. Okay. So here's some comments from past years. Well, this one is not such a. Okay. Comments from past years' course evaluations. The course was very, very thorough. What wasn't covered in class was covered on the final exam. So now, so let's. That's a short one. We have a lot of material today. So you shouldn't cheat, right? Because you know why you shouldn't cheat? Because it's bad. Well, maybe. Oh, I know what the problem is. Oh, yeah, it's bad. Okay, there you go. Okay. Homework policy. Okay. Rules are simply, you may work together using sources. What you turn in is in your own words, written in solitude, right? I mean, this should be, is there really confusion here? Okay. Okay, so this should not, it should be clear what the rules are, okay? Okay, so now we're going to talk about this other problem called bipartite matching. Here we're given a graph, and we're given two sides of the graph. In this case, the graph is on 8 nodes, and there's 4 nodes on the left and 4 nodes on the right. So this is what L and R signify. Okay, so the left nodes and the right nodes, and these edges in this particular graph, these edges indicate who is compatible with who. In other situations, the ones on the left may indicate jobs, and the ones on the right may indicate people. Okay, and it may say who can do what job, and it's an assignment of jobs to people, right? And so what you generally want to do here is you want to find the maximum. In this particular example, it's clear you want to find the maximal number of pairs who are compatible, right? Does that make sense? Okay, so what do you think the maximum number of pairs that are compatible here? Well, there can't be more than 4, but is it clear there's 4? Okay. Okay, well, let's just try it. Okay. What happened here? How come it's showing up? Okay, it just looks like it's showing up. Oh, weird. Okay, so we can match Cindy to Ollie. We can match Jen to Ivan. We can match Shelby to Chen. And look, Katya doesn't have an option here, right? What? So you see, this seems like it's not, right? What do I do now? Jen should go to Jock. Okay, so this is the problem, right? Katya only has one place to go. So Jen, but this creates a problem if we matched Katya to Ivan. So we need to stop. Ivan has to. Jen has to go elsewhere, right? You can't match to Ivan, and Jen can match to Jock. Okay, did you see what we did there to undo? We sort of started with some sort of greedy algorithm. Well, let's just try it. Let's try this. Let's try this. Okay, we create a problem, right? And then we sort of undo a little bit of what we did before, right? So we could actually make an algorithm out of that, right? We can sort of start thinking about algorithms here of how we solve this matching problem. Again, the direct greedy algorithm doesn't work right away. But you could almost see the problem here. You can say, well, Katya has nowhere else to go, so somebody that she needs to match to, somebody she's willing to match to, they need to sort of tell the people they're matched to go somewhere else. Okay? So there's this sort of undoing and doing and undoing. Okay, so we can start deriving an algorithm, but let's do something a little bit easier. Okay, we're going to do an algorithm by reduction, right? Christos said a couple of lectures ago that this is the lazy man's way to do algorithms, or a lazy person's way, lazy man's way. So what we're going to do is we're going to take our matching problem and we're going to write down a flow problem. Okay, and then from the flow solution we'll produce a matching solution. Okay, so that's one way to do it. We've been doing a lot of, in some sense, reductions. We give you a problem, and we tell you to write down a linear program. So this is a bit different because we tell you there's 5 objects, and they each cost this much, and blah, 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 and then you write down a linear program. This is a general way to do that. You give an input in a certain form, and I can write a program, essentially a program, to translate it into another form. And then I call the subroutine that solves that form. Okay, so we have in particular, we have an algorithm that solves maximum flow problems, right? Does everybody know it? Okay, so let's look at our matching algorithm. This is the same graph as before. I just used only first letters. So we want to take this matching instance, which is a graph. It's an undirected graph. And we want to transform it into a maximum flow problem. So you guys know how to do that? Any ideas? How would you transform this into a maximum flow problem? Any ideas? Any questions? Yeah. Right. Yeah, that's good. So yeah, so what he says is, he gave me the reduction. So one thing to do a reduction is you want to think about the power of the two things. What do you want here? You want each node on the left to pick a node on the right. Okay? And you don't want any node on the left to pick more than one node on the right. Right? So you can sort of think of saying, well, every guy on the left wants to route one unit of flow to some node on the right. But no node on the left should route more than one unit of flow. And no node on the right should receive more than one unit of flow. Okay? So that's one way to think of matching. Once you have a matching here, you can think of this matching as saying, Cindy is going to give Ollie 1 unit of flow. Jen is giving Jacques 1 unit of flow. Katya is giving Ivan 1 unit of flow. And Shelby is giving Chen 1 unit of flow. And each guy, each girl sends 1 unit of flow, and each guy receives 1 unit of flow. Okay? That's not, you can sort of translate it and think that's what's happening here, right? Okay, so that's what we're going to do. We're going to say that we're generally sending flow from the left to the right. Okay, so we're going to direct our arcs from left to right. And now each source, I'm going to put a capacity of 1 on all these arcs. Each girl receives 1 unit of flow from the source. Okay, and each boy gets 1 unit of flow. Okay, so now the max flow here is the total amount of flow through this network is at most 4. I should have colored that last one blue. It's unfortunate that one is also labeled S, but so the max flow, it's a capital S, I guess. Max flow equals the maximum matching size. If you route 4 units of flow from S to T, that means everybody on the left received 1 unit of flow. So if it received it, it had to get rid of it. So it had to use one of these edges in the middle to get rid of it. That's the only way any node in here can get rid of a unit of flow. Is by all the out arcs are only these arcs, right? So if it gets 1 unit of flow, it has to get rid of it. So that means it's matched. It has 1 arc leaving it. Okay? And this one, if it has an arc leaving it, it must mean one edge came in. Okay? So it says this is matched. Every node here has 1 unit coming in. If it has a unit of flow coming in, it has 1 unit of flow coming in, and it's matched. If it has a unit of flow going out, it's matched. Okay? So the maximum flow value equals the maximum matching size. Okay. So there's a problem with this reduction, is that the matching was saying I want to match, these 1 to 1. I don't want to match half of Jen to Jacques and half of Jen to Ivan. That might create issues, right? Okay, so this is right. So this is actually a problem to do this. And I said before, and we know the flow max flow may, we didn't argue yet that it's integer. It has integer values. Except we did. Okay, so if we write it down as a linear program, there's no reason particularly. There is a reason to know that it solves the integers, but there's no reason, we haven't argued yet that the flow is going to be integer. Okay, so this is not a perfect reduction. We've reduced from a problem where we want to find a set of objects to a problem where you could sort of do these things fractionally. Okay, but why do we know that we can find a flow that's integer? Does anybody remember why or think about it? Yeah. Right. Okay, so if he says the way the algorithm runs, okay, so now you think back to the algorithm. What did our algorithm do? Every time the Ford-Fulkerson, the augmenting path algorithm, this is this Ford-Fulkerson algorithm, every time it found a path and routed as much flow as possible, okay? And what are those flow values going to be? What's as much? Is there any way for you to get a fractional as much flow as possible? No, because if the original inputs are integers, the flow values are only going to, the capacities are going to be integers, and the residual capacities are, 5 minus 4 is 1. That's an integer. 6 integers are closed under addition and subtraction. So you're only ever going to get integer values on all the edges, and you're only going to use integer values on the augmenting paths, and you're only going to get integer values of flows. Okay? So that says, in fact, the max flow algorithm that we already described actually solves a stronger problem than just max flow. It solves the integer max flow problem. Okay? Okay, so now we're going to go on to another concept, which is duality. Okay, so let's look at this linear program. So we have this linear program, and anybody see what the optimal is here? Why don't you try to think what the optimal is? I'll give you a minute to get engaged or something. Okay, who thinks they know the optimal? Just raise your hand if you think you know it. Okay. Who thinks they don't know the optimal? Okay. Who doesn't have a hand? Okay. Who's not sure? Okay. So everybody raise their hand. Let's see if that works. Raise your hand. Okay. Good. Okay. Okay. Good. Just making sure. Okay. So, anybody the optimal? What do you think it is? What's the optimal value? 3. X2 gets 3 and X1 gets 1. Okay. So what's the value of that? Okay. So X1 equals 1, X2 equals 3. That's a solution, at least. Well, let's see if it's a solution first. So if X1 equals 1 and X2 equals 3, X1 is 1, 1 is less than 4, so that's valid. X2 is less than or equal to 3, so that's valid. 1 plus 2 times 3 is less than or equal to 7, so that's valid. So it's a legal solution, right? And now the value of the solution is 25. I just plug in 1 plus 8 times 3, which is 25. Okay? So this is a solution. So is it the optimal solution? Yeah, it is. Why? Because it's the optimal solution. Okay. So it would be nice for her to say, you're just duhing me. Duh, it's the optimal solution, right? Okay, so I don't really like to be duhed. I'd rather actually know its optimal solution and have some easy way to check. And maybe you won't think this is easy, but like max flow, right? When I wrote down max flow, I could tell whether it was optimal solution by writing down a cut, right? And that was nice. If you give me a sorted list, I could tell it's sorted by just checking each neighboring element. So here, how do I tell its optimal solution? Well, in some sense, I need to go solve the whole thing again. I don't really see how an easy way to do it. Okay, so let me show you one way. One way to do it is prove an upper bound. So what does proving that this is optimal mean? It means I want to prove that you can't get any higher for any valid solution. Okay, so I want to show any valid solution can't have value better than 25. Okay? Okay, so how might I do that? Well, okay, so one thing is I say if it's a valid solution, I have these equations that x1 is less than or equal to 4 and x2 is less than or equal to 3. I know that has to be true for any valid solution. Okay, so and I know the value of a valid solution is x1 plus 8 times x2. So can I derive an upper bound on x1 plus 8 times x2 using these equations, right? x2 has an upper bound, x1 has an upper bound. Is there a way to now give an upper bound for x1 plus 8 times x2? Yeah, so x1, if I just take this equation and I add, and x1 plus 8 times x2 has to be less than 4 times 8 times 3, right? Because x2 has to be less than or equal to 3, right? And x1 has to be less than or equal to 4. So therefore, x1 plus 8x2 has to be less than or equal to 28. Okay, so now I know at least I'm not farther than 3 from optimal, right? And so a generic way is I knew an upper bound on x1, I knew an upper bound on x2, so I know an upper bound on the sum. But more generically, what I did is I added equation 1 and 8 times equation 2 to get an upper bound. Okay? And when I added equation 1 and 8 times equation 2, what I got was the optimization function on the left-hand side. And on the right-hand side, I got 4 plus 8 times the right-hand side of this equation. Right? If I add two inequalities, I add the right-hand sides, right? And I add the left-hand sides. Okay? When I add them. When I multiply an inequality, I multiply this one side and this side. Okay? They're both valid. These inequalities remain valid for any valid solution. Right? Multiplying both sides by 8, if it was valid before, it's still valid. Okay? Adding these two equations says x1 plus x2 is less than 4 plus 3. Right? So this is one way to provide an upper bound on this value if I can add up the left-hand sides to be the optimization function. Then I get a right-hand side which is an upper bound on the optimization function. Okay? That's pretty cool. I think that's cool. Okay? Okay, so loosely this is essentially what we also did for the min-cut problem. Okay, we're adding up equations to build the cut. But so now there's so is there a better solution? So still, the upper bound on the solution is 28, and our solution value is 25. So we still haven't proven that our solution value is 25. Does somebody see how to prove that the solution value is at most 25? Yeah. Yeah, so he said to add 6 times the second inequality to the third inequality. And I'm going to show you that on the next page. But, really, if you could do it in your head, then you're going to be more engaged. So do you see that? So 6 times the second inequality will be 6 times x2 is less than or equal to 18. Okay, now you add 6 times x2 plus x1 plus 2 times x2. So now you have 6 x2s and 2 x2s. So you'll have 8 x2s. Okay? So you'll have x1 plus 8 x2 is less than 18 plus 7, which is 25. Okay? So there might be a better solution. There might be a better upper bound, but he gave away the game by saying, showing us a better upper bound. So let's look at the better upper bound. So again, the solution value is 25. So you add equation 1, and it should be 6 times equation 2. And then you get this bound. Oh, that's what we did last time. Well, that's what we did last time. We added equation 1 and 8 times equation 2, and that gave our bound of 28. And is there a better way to add equations to get a bound on the function? And we just derived it. So 6 times equation 2 and 1 times equation 3. So again, 6 times equation 2 would give you 6 x2s And 1 times equation 3 gives you 2x2, so you get an 8x2 here. And 1 times equation 3 gives you an x1. So on the left-hand side, you get x1 plus 8 times x2. On the right-hand side, you did 6 times equation 2, which would be 6 times 3, and 1 times equation 3, which is 7, which is 25. So yeah, I think I had a different example. I'm sorry. So, okay, yeah, so what's the problem? Okay. Okay, so what's the idea? In this example, you're adding up a positive linear combination. Now, it was important that we multiplied by a positive number. If you multiply two sides of an inequality by a negative number, what does it do to the inequality? Flips it. Okay, it's no longer valid as an upper bound to your left-hand side. Okay, so it's important that we added up positive multiples of each row to get our upper bound. Okay? I mean, if you multiply by a negative, then you get a lower bound. And that's not what you're trying to do for maximizing linear programs. Okay? Yeah, but the equations will be the other way too. The equations will also be the other way. I'll show you. Okay? So what he said is if it's minimizing, it'll be the other way. So generally, a typical linear program, if you're doing a max, you write the inequalities as less thans. Okay? Because in general, if you want to maximize something, raising these values is what you want to do intuitively, raising these values on the left. And that's why you have less thans here. Because otherwise you could, if it's greater than, max is sort of easy if you just try to make things bigger and bigger. Then maxes get bigger and bigger. So that whenever you have a max linear equation, you write the inequalities, except for the non-positive ones, as less thans. Okay, this is the standard form. Yeah, you do it the other way. Okay, will this always work? Will this always give you the best upper bound? So here in our example, I showed you an example where we wrote down a solution, and then I proved to you it's optimal. In a rather simple way. I just added up the equation and said, look, you can't do any better, right? You should be totally convinced at this point that you can't do better than 25. Okay? Okay, so the question is, there's two questions that arise. Will this always work? Can you always find an upper bound this way that equals the value of your solution? And another question is, if you can always find an upper bound, how do you do it? How do you find a better upper bound? Okay? Okay, so let's look at this. Let's look at this as what this process is. So what we're doing is we're going to try to figure out how to compute the best upper bound. Okay? We're going to defer whether we can find whether the best upper bound matches the lower bound right now. So what we did in the previous process is we multiplied each one of these equations by a number, y1, y2, and y3. Okay, so y1, for example, the upper bound we chose, what do we choose for y1, y2, and y3? So the first time we added 1 times the first equation plus 8 times the second equation. Okay? So that would say y1 was 1, y2 was 8, and y3 was 0. Okay, and then we got a new inequality, right? We got an inequality x1 plus 8 times x2 is less than or equal to whatever that would be. Okay? So in general, if I think of this as a process, what I get is that if I add up these equations with these multipliers, I add up y1 times the first inequality, y2 times the second inequality, and y3 times the third inequality, I get a new inequality. Right? And what does that new inequality look like? It looks like, it's a little off. Okay, so it's y1 plus y3 times x1. Okay, and this should be y2 plus 2 times y3. There's an error here, so let me put that here. Okay. So this line should be as follows. This line, right, the line at the bottom should be okay, y1 plus y3 times x1, right? Because I'm doing y1 times x1 plus y3 times x1. y2 doesn't have any x1 in that equation, inequality. So there's not going to be any multiple of x1 that corresponds to y2. Okay? Plus, let's get that off. Okay, since it's wrong anyway. So now what's the next one for x2? What is the coefficient for x2 going to be? y2 plus 2 y2 times x2. y3. Did it again. Times x2. Okay, that's going to be my left-hand side. Okay, now my right-hand side is going to be what? Right? 4 times y1 plus what? Plus 2y2 plus 7y3. So I obtain another inequality by adding up these things. And by choosing the y's in various ways, I actually obtain a lot of inequalities, right? This gives me the flexibility this tells me all the inequalities that I can, all the valid inequalities. You know, any valid inequality, I can write down y's that correspond to it. Okay? Okay, so now, now if you want to prove an upper bound on the optimization function, what we wanted before was we wanted the coefficient here to dominate the coefficient to be 1, right? Last time we wanted it to be 1 times x1 plus 8 times x2 was our last example. Okay, we wanted this number to be larger than the coefficient of x1, and we wanted this number to be at least as large as the coefficient of x2. And then this right-hand side would actually give us an upper bound on the optimization function. Okay? So in that case, we wanted y1 plus y3, and the optimization function for this problem, the coefficient of x1 in the optimization function was 1, and the coefficient of x2, this should be y2 plus 2 times y3, should be greater than 8. Then x1 plus, if you have these coefficients for any set of y's, where y1 plus y3 is greater than or equal to 1, and y2 plus y3 is greater than or equal to 8, you have that this expression is upper bounded by this expression, which is the function of the y's. Okay? So as long as we have these two conditions, we get a valid upper bound. Yeah? Okay, when you multiply an inequality by a negative number, you reverse its order. Okay, so let me show you why that's important. Let me see if I come up with an example. So 2 is less than or equal to 3. 1 is less than or equal to 2. Is that going to work? Okay, so now I multiply this by negative 1. Right? So now I get negative 2 is greater than or equal to negative 3. So what do I say here? If I add these equations, what do I say? Is it less than? Is it greater than? Right? There's a problem here, right? Because you have that 1 is less than 2 and negative 2 is less than negative 3. But you don't know, if you add these two, well, I don't know, we can do it. But negative 1, negative 1. I guess it happens to be less than. But let's multiply by negative 2. So now you get negative 4, negative 6, and you get negative 4 here, and negative 3. So this is not a valid inequality, right? Because negatives are bad for inequalities. They're not bad for equalities, right? You can multiply both things. For equalities, you can multiply negative 1, both sides by negative 1, everything's fine. But for inequalities, it switches the direction. Okay, so it wouldn't be a valid upper bound. Okay, so find best yi's to minimize the upper bound. Okay, so this is the problem. This is the way to find the best upper bound. What I want to do is I want to find y1, y2, and y3, where y1 plus y3 is bigger than 1, and y2 plus y3 is bigger than 8. And I want to minimize this. The best upper bound is the smallest value of this, where these three conditions hold. Does this look familiar? How would we solve this problem? Do you guys know how to solve this problem? It's a linear program. Right? Right? These are all just variables. This is a linear constraint. This is a linear constraint. And this is a linear optimization function. Right? So fine. Again, so we want to do this. So we can minimize. What we're trying to do is minimize this right-hand side here, subject to a few constraints. That y1 plus y3 is greater than or equal to 1, and it should say y2 plus 2 times y3 is greater than or equal to 8. Okay? So subject to those two constraints, we should try to minimize this value. Okay? So we started with the linear program, and we said, okay, well, let's try to find the maximum solution. Here's another linear program. So the upper bound, and this linear program provides an upper bound on the maximum solution. So these two linear programs are very related, right? Okay, so they're a linear program. From the original linear program, you can derive this linear program just like I did. Okay, so it's called the dual linear program. So the primal has value x1, it has these this is the solution, x1, x2, 1, 3. And here I think it was, this is the right solution here for the dual. So this is a linear program, right? We found the solution to this before by hand, right? Where we added up 6 times the second equation plus 1 times the third equation. Okay? And the value of both was 25. So the primal is optimal. Why is the primal optimal? Because this linear program is an upper bound on the value of the primal. That's how we derived it. We wrote it down to be an upper bound. We said, well, it's a way to add up the equations in the primal so that the optimization function is dominated on the left-hand side. And the right-hand side is the value you get out of that process. And then we wrote it as a linear program. So this linear program is an upper bound on the value of the primal, and we got a value of, we have a solution here of value 25. That's an upper bound on the value of this. So now we know the primal is optimal. Now let's say we're really interested in the dual. Do we know we have the best value for the dual as well? So now this is just another linear program. Now just think of this separately as the problem I'm trying to optimize. How do I minimize this? Do I know that the value of this is no less than 25? Do I know that the solution is the optimal solution for this dual linear program? What do people think? Yes? Yeah. Okay, no? I don't know? Okay, so, the dual is optimal too. Why? Well, the dual, any value of the dual is an upper bound on the value of the primal. So if you have a value of the dual that's equal to the value of the primal, that means the dual can't be any lower, right? It's an upper bound on any value of the primal. So given a dual value that's equal to this, it's the same as the min-cut max flow algorithm. Okay, so, is that clear? Okay, so it's the same argument as the min-cut max flow. If you have a max flow whose value is equal to the min-cut, to a cut, that if you have a flow whose value is equal to the value of a cut, then the flow is optimal because it can't be larger than any cut. Okay? And the cut is optimal because it can't be smaller than any flow. Okay, so this is the same statement. In fact, max flow and min-cut are duals. They're dual linear programs. Okay? So Yeah.
Explain why exactly you select y1 plus y3.
Oh, because yeah, I can. Yeah, so here, let's do that. Okay. It's why do I have y1 plus 2 y there because of this 2 here. It's y2 plus 2 y3 because I'm trying to compute the coefficient of x2. So if I add up y2 times the second equation, the coefficient of x2 will be y2 times x2 from the second equation. And the coefficient of x2 from the third equation will be 2 times y3. He asked why is it y2 plus 2 times y3 on this board here. Okay? So yeah. Okay, so okay, so now this may make you a little nervous, but really, so we can write this in matrix form. A is just a matrix, and x is your vector of variables. So A times x is less than or equal to B. That's our primal. And it was maximum C times x. It seemed kind of laborious for us to derive the dual. It seemed like, okay, well, what do I do here? What do I do here? All I'm doing is taking a transpose. Okay? So really, in matrix form, it's very easy to do what I did. Is now, where you had variables x here, you have variables for each column here. Okay, each row here corresponds to an inequality. Okay, so this matrix has a row. Let me write it out. This matrix A is a row, and it's A11, A12, A1n, and you have a variable x, and you're less than or equal to some b1 through bn. Okay? Okay, so this is what the primal LP looks like. Okay? And now the dual is just it says, well, it's a way to add up equations. So for each value, for each variable in the dual, you get one variable for each row in this matrix, right? Because you're assigning the yi's are ways that are things you're multiplying each equation by. So the dual is exactly, write it out. And you want to maximize C times x, right? This is a function here. In the dual, what you want to do is you want to take y, which is some vector like this, and you multiply by the matrix A, and you want it to be bigger than this vector C1 through Cn. Okay? And now you want to minimize the right-hand side you get. Okay? So this is what we did. The yi's were ways to add up the equations. So it's a transpose. It's this transpose here, this operation of y multiplied by a is just giving you some linear sum of the inequalities. Okay? And you want, and so this translates into this particular set of primal and dual programs. Okay? So, yeah. It should be a min. Sorry. This should be a min. Very, very good. Okay? So that should be a min. Okay, so now rules. Okay, so rules for school is rules for taking duals. So what do you need to do? What's the process? So this is, okay, especially this needs to be a min. I'll correct it when I put it up. Thank you. So let's write out sort of intuitively. Matrices are fine. You could always put it in a matrix and do it. But the way we wrote out our expressions for example, for max flow. Here's this linear program. Here's a set of linear equations. Okay? Linear inequalities. Okay, so and you want to translate them into a dual. So at some point in the homework, you're going to be asked to show that min cut and max flow are duals. So the way to take a dual, sort of at least with the variables that actually have meaning to us, is, so this is a standard way, is the dual of this program, A, x is less than or equal to b, you're maximizing c times x where x is positive. The dual is this transpose. You take this transpose, where you used to have less than or equal to, you have a greater than or equal to. Where you used to have a max, you have a min. Okay, so min goes back and forth to max. Greater than get back and forth to less than. Inequalities go to non-negative variables. So for each inequality in the original primal, you have a variable in the dual, because the dual variable is telling you how much you add this inequality in. Okay, so for each inequality in the primal, you have a variable in the dual. And for each variable in the primal, you have an inequality in the dual. So the dual variables, when you add them, you want to say they dominate the contribution of that variable to your optimization function. Okay? And now, in general, so in the standard form, there's no equality constraints. But you know, for max flow, you have an equality constraint, right? You want to say the sum of the flow into a node is equal to the sum of the flow out of the node. So for inequalities, when you look at the corresponding variables to that inequality, they're non-negative. But for equalities, they can be positive or negative. Okay, so the equalities go back and forth to unrestricted variables. Okay, so if you have an equality, you have a constraint where you have an equality, the corresponding variable in the dual could be either positive or negative. Okay, or zero. Okay, so this is just something you'll want to keep in mind. Okay, when you're taking duals, these are sort of cheat sheet on how to do it easily. Okay, so now let me give you a break. Okay.
Question: how did you get from this equation that had all the y variables on the left-hand side, and you said that you said that y1 plus y3 has to be greater than or equal to 1, y2 plus 2y3 has to be greater than or equal to 8?
Yeah, if that's true. If that's true,
right,
then this is a valid upper bound on the.
Right. So how did you come up with this?
Well, if y1 plus y3 is greater than or equal to 1, then the left-hand side here is bigger than 1 times x1.
Right.
And it's bigger than 8 times x2.
Right.
If these two equations hold.
Right.
That's how I got from there.
So why would you want it to be bigger than 1 times x1 and bigger than?
Well, because if it's bigger than these two, bigger than or equal to these two, then this whole upper bound is valid. Okay, you get this upper bound, right?
Yeah.
So if you plug in these two, if you plug in something, you could plug in, so this number is bigger than 1. So I can replace it by 1. And this inequality is still valid. I could also replace it by 8, and this inequality is still valid. Right? Because 8 is y2 plus 2 times y3 is bigger than 8. So this equation, you could always replace what you multiply by a lower number. Right? If I say 11x is less than or equal to 20, I also know that 10x is less than or equal to 20. Right? So now I can say that this it could be, it's definitely true. If this is true, this is definitely true. Right? And why do I care about x?
So then you also use these as your other.
Yeah. Then it says this is, therefore this is definitely less than this if these two constraints are hold. Yeah.
Okay.
Right. But you have to make sure those things hold.
Right. So
And that's why you use a linear program. Yeah. Okay? Does that make sense?
yeah.
Okay.
Thanks.
Yeah.
I was with you, like the whole thing except for this.
Oh, okay. This is just a way to write it as a matrix. So,
Does that mean if there's a lot of constraints?
well, it's just, yeah. Normally the way you get an input is as a matrix. Somebody gives you your matrix of constraints. Remember 110 or something? Yeah.
I think it could be more.
Okay, I see.
I mean, I understand what you're saying. It's
Right.
just what does X represent? Is that
X1, yeah. I'm sorry, X1.
those are your variables?
Yeah. Yeah.
And
These are your inputs. These are coefficients. Yeah.
for the primal,
Yeah. Okay, so for our example,
which are less than or equal to something.
yeah, so for our example in matrix form, yeah, let's look at our example. Yeah, so let's look at our example. It's less than or equal to, was it less than or greater than? Less than. 4, 3, and 7. Right? And the equations were 1, 0, 0.
Your primal, or if you're doing min in your primal, then your dual is
Oh, there was only 2.
if you're doing
Yeah, max in your primal, you're doing min in your dual. And here,
your primal, then max is your dual.
yeah. Okay? So this is our set of equations, right? Do you see why? Because this is x1 is less than or equal to 4. Okay. So now the dual would say you put y1, y2, and y3 here. Right?
The A remains the same as the coefficients.
Yeah. The A is the same because you're adding up the equations. Okay? So the dual for this and now you maximize. Yeah, so here, let's write it the other way, yeah. So this would be the max x1 plus 8 x2. Okay? So let's write it. So now you get y1, y2, y3, which is
So those coefficients correspond to the optimization function.
okay? Okay, so I just wrote out the equations as a matrix, and then I wrote out the dual as a matrix. The matrix in the middle is the same. We're just multiplying by the transpose. The B vector here is the B vector there.
So these become coefficients.
Yeah.
Do those just pop out after
Which becomes, yeah, these become the right-hand side. Because here you're adding up equations, you're adding up these equations. So you're getting the right-hand side here. y1 times 4, y2 times 3. Here, I'll go over this. Okay. Okay, so let me go over this matrix form a little bit here. Just, this is our example. I just wrote out the matrix for it. Okay? So our equations were x1 is less than or equal to 4. Okay, 0, 1 times x, this row times this column. x2 is less than or equal to 3. and x1 plus 2x2, right, is less than or equal to 7. So you write them out as a matrix. Okay, that's what this AX is less than or equal to B is. This is the matrix A. That's your input. B, that's an input. And the optimization function is x1 plus 8x2 in our example. And the input is 1, 8, and the variables are x1, x2. This is equal to the vector, this vector, dot this vector. Okay, so that's what this is saying. AX is less than or equal to B. This is the vector B. This is the matrix A. And this is the optimization function C. Okay? Okay. And the dual, similarly, is this matrix A, same matrix, but you're, instead of multiplying, instead of having this set of equations here, inequalities, what you're doing here is you're adding up these equations, right, in the dual. So really what you're doing is you're multiplying from the left, you're summing up inequalities here, columns. Okay, so if you write out these terms, you'll get the dual program. Okay, and what gets switched is the right-hand side here in these inequalities become the coefficients of the optimization function, right? We wanted the coefficient. This column is in this picture is the coefficient of x1. And what we want for our dual to be is the coefficient of x1 to be larger than the coefficient in the optimization function, which is 1. Okay, so this is exactly illustrating the intuition for deriving the dual. Okay? Okay, so, let's go on to... Okay, so now we're going to talk a little bit about these things called strategic games. So strategic games are games where each person has to decide on a strategy to play against the other person. It's not like chess where I make a move, you make a move, I make a move. It's not like a board game. It's, let me give you an example. So each player had a strategy set. Okay, so there's some complicated notation, but let me just give you an example. So each player has a strategy set, and depending on what all the players do, everybody gets a payoff. Okay? So let me show you an example. So player 1 is two players are playing this game. Okay, so they have two strategies. They could either cooperate with each other, or they can compete against, they could defect. Okay? So they're captured by, they're in jail, these two players, and they could either, I guess that's not the right thing, but you could either, there's two spies, and these spies stay together with each other, or these spies defect to the other side. They're captured by the bad guys, or their enemies. Okay? So now if the spies cooperate, they get in some trouble because they've been captured. But if they don't cooperate, if one of them defects, then that guy is better off. But the one who doesn't defect is screwed because the guy who defects narcs him out. Okay? So this is an example of the game. So let's see what the payoffs might look like. So if they both they both cooperate with each other, they don't defect to the other side, they both get paid 3. They sort of benefit. Eventually their own government buys them back or something. Okay? But on the one hand, if player 1, this is player 1, this is player 2, if player 1 decides to defect to the other side, he gets paid 5, and player 2 gets screwed. He gets nothing, right? Or these could be a big negative number, right? And on the other hand, if they both defect, they're both kind of screwed. Okay, and they're not quite as screwed as if one person defects and the other person cooperates. But if they both say, okay, I'm guilty, take me away, that they both get a little better off from the time when one person accuses the other one. Okay, so this is called the prisoner's dilemma. Okay, you have to decide whether to cooperate with your comrade in arms or defect to the jailer. Okay, does that make sense? So what do you think they'll both do? What should they do? What will they do? Yeah. Why will they defect? Right. Right. So what he said is the better option in whatever, let's say you think the other person's going to cooperate, right? If player one thinks this guy's going to cooperate, what should he do? He should defect, right? Because he gets 5. On the other hand, if player one thinks the other guy's going to defect, what should he do? Defect. Okay? And this is symmetric. So this is very sad, right? Yeah. Well, if you go to jail... Okay, so what is it supposed to model? Okay, I'll tell you in a minute. No, I'll give you an example. No, I promise I'll give you an example. So, okay, so why is this famous? Okay? What's the best thing for the players to do? Clearly, it's to cooperate. They both get 3-3, but they won't, right? If player one wants to do better, if I know the other guy's cooperating, what's the problem for player one? He's going to say, hey, look, if I defect, I get better. Okay? So that red thing there is danger. I shouldn't stay on the strategy, cooperate. So I move. Okay, so now that I'm here, what is player two going to do? For player two, what is it better for him to do? Go over to defect. Okay? Because right now, player two sees there's a better option for him given that player one does this. So he defects. Now it's stable. 1-1 is a stable solution. It's very sad, but it's stable. Okay? So this is called the Nash equilibrium. This is a game, a strategic game, where neither player has any incentive to change strategies. Right? People see that? Okay. So what? This is a digression. It's like, what is this? This whole thing is a bit of a digression from what we're doing, but I think it's really what compels and underlies the next part of what we're doing. Okay. So this is called prisoner's dilemma. Two prisoners are separated by jailers and asked to betray partner. It's also the basis of the free market. Okay. Do you see why it's the basis of the free market? Yeah. Yeah. Right. So he's saying, say I have company A and company B, and they both make shoes. So if they cooperate, and they're the only ones who make their shoes, if they cooperate, they can just say, okay, let's raise prices. It's called a monopoly. And for them, they're just going to keep raising prices, right? Why don't they do that? Because one of them is going to notice, yeah, my prices are high. If I drop my price by a little bit, I'm going to get more volume. Okay? And the other guy says, oh, if he's going to drop his price, I'm going to drop my price. Right? That's why we get efficiency in our market. Or at least that's the theory. Right? Right? So this is the basis of the free market. This sort of competition, this game theory, this strategic game theory, where there's many players in the market or in your society, and they have various strategies available to them. They only keep their strategies. Yeah.
This situation assumes no collaboration, because if the prisoners, for example, know.
They know, but there's still some incentive for them to. I mean, it's true. But this is why economists say, okay, this is why we have efficiency in our market. I think they don't. Economists are smarter than that. They really know there's something more complicated. Okay, so this says there never should be a monopoly where they collaborate, right? That's what it says, and you're saying, well, that's just crap. Well, you didn't use that word. Okay, I'm sorry. Okay, so there are monopolies, right? There's OPEC, sometimes airlines are. It's much more dynamic than that, right? So this is not a pure model, but it's one of the basis of why, of understanding how people behave, or people or entities behave. Okay, so OPEC, you can make a lot more money. They have to have stiff meetings to make sure that one doesn't ramp up its production. Right? They do this. They force a monopoly with various outside measures, but they do it, and they're able to do it, and they make more money by doing so. So they should defect. Why don't they? So what this says is the basis of the free market economy, which is this prisoner's dilemma. Really, it's this notion. It's almost a religion that companies compete, right? And that's why you get good prices for what you get. Okay? It's not so much, right? It's not such a good argument. There's counterexamples that they abound. Okay? So there are more sophisticated models, much more sophisticated models. In particular, where this prisoner's dilemma was introduced by the first, it was a mathematician, I think it was Shapley. He introduced this, but he also anticipated all the problems with it. Unfortunately, most people only read the first part. So there's all different notion of coalitions is what you're talking about, and complexity. So there's lots of interesting game theory. In fact, Christos is a big, in economics they study this a lot. Okay, it's really the notion of how do people behave in the common environment with various strategies available to them. This is what economics is. Okay, and Christos, in computer science, it's been receiving a lot of attention, largely maybe founded to some extent by Professor Papadimitriou. He looks at these things as with a complexity. Okay, so in addition, the players, in addition to figuring out their optimal strategies, is they have to figure out their optimal strategies. And some of these figuring out of optimal strategies is an algorithm. So you can't just say these guys are competing, they do the best possible thing, because they actually have to figure out how to do the best possible thing. And once you bring that into the equation, it changes the whole dynamics of the interaction. Okay, and that's one of many things that Christos works on. So in our context, we're going to look at a simpler example, and we're going to get at how do you compute the optimal response, okay, in a particular type of strategic game. Okay? And so now again, there's two players. Each player has a strategy set. So player 1 may have M strategies, player 2 has N strategies. So here, in a zero-sum game, what it means is if I play 1 and you play 2, I pay you $1. Or maybe if I play strategy 3 and you play strategy 4, you pay me $1. Okay? So between us, nobody gained. For any pair of strategies, nobody is benefiting. Together, one of us might pay the other, but nobody's making money or losing money. I mean, the two of us together are not. That's what zero-sum means. It means the payoffs for player 1 is the negative of the payoff for player 2. That's what zero-sum means. So now, the payoff, so you can give the payoff by a matrix again. So the row, we're going to think our canonical version of this is the row player is maximizing and the column player is minimizing. Okay? So you can think of each entry as the column player, you have a matrix, and the column player at entry, here, let's look at it. Here's a matrix. At this entry, if I play R, if the row player plays R and the column player plays P, the column player pays $1 to R. Okay? On the other hand, this should be, if the column player plays S and the row player plays P, then the column player pays -1 to the row player. Okay, or another way of saying that is the row player pays 1 to the column player. Okay, so these are more or less losses and wins. This matrix should have a -1 here. Where should it have a -1? Do people know? This is Rochambeau. So rock ties with rock. Rock loses a paper. It should be a -1 here. Okay? And rock beats scissors. Okay? Paper beats rock, so the row wins here. Paper ties with paper, so nobody gets paid here. Paper loses the scissors, so row pays 1 to the column. Okay? And the scissor, the same. Okay? So this is a matrix. This is a game we play. It's a strategic game. Each one of us has to have a strategy to play against the other person. So we want to play a strategy against each other, right? So what is the notion? So is there any Nash equilibrium here? Is there a strategy I could have and you could have that will be stable, that we don't have incentive to change? So the answer is no. It doesn't look like it, right? So let's try a few. Let's say, but player 1 plays rock and player 2 plays rock. They're both playing rock. Does either one have incentive to change? Yeah, they both have incentive to change. Player 2 wants to go here and player 1 wants to go here. This should be a negative. Okay? How about now? Let's pick one of these. Is this a stable place? Is this a stable point? Is this an equilibrium strategy? No. Right? Because player 2 wants to go here and player 1 would want to go here. Okay? So it just keeps cycling. So now if you're here, you want to go to another place. So there's no stable Nash equilibrium here. Yeah. Right. Okay, so this has this notion, these are called pure strategies, that this notion that I'm only going to pick one strategy. But what do we really do in Rochambeau? We know the value of this game. It's a boring, stupid game, right? We know nobody gets a benefit. What do we always do in Rochambeau? Yeah, you just play randomly. So now we have to have a stronger notion of what strategies are. Instead of saying a strategy is, okay, I'm going to play defect or I'm going to play, you want to say, I have a probability of playing these things. And the reason I can't do better than playing this probability is I know you're playing a probability. Okay? And I may know your probability distribution, but given certain probability distributions, maybe there's a way, if you give me your probability distribution, that I know I have no incentive to change. Okay? So these are called mixed strategies. So here you want to say, what's player 1 really going to do? He's going to play uniformly over these three strategies. 0.33, 0.33, 0.33. That's what you do, right? That's how you play rock, paper, scissors. So now instead of thinking of player strategy as a row, you think of it as a probability distribution over rows. Okay? And if you're scared of probability distributions, just say they're numbers assigned to the rows so they add up to 1. Right? That's all the probability distribution is. Okay, it's the probability I play 1, the probability I play 2, and the probability I play 3. And I add them up, they better be 1. I have to play. Okay? So, and this is the probability distribution for the column. Now we want to say, well, what's the payoff here? What do you expect to get here? You can't just read off an entry in the matrix anymore and say, oh, this is what the value is to player 1 and the value is to player 2. Okay, so you have to figure out what this value means. So how do you figure out the value to player 1 of this game, which is the negative of the value of player 2? So how would you figure it out with these things? We know the value of the game. What is the value of the game? Just from experience, what's the value? 0, right? Nobody gets anything on average. So we should be able to get that from this matrix. So each player is playing a pure strategy. This is what a pure strategy. Each player basically only plays one. Okay, so now let's look at the payoff. You can't just look it up in the matrix. So you want to think of the average payoff, right? So each person plays a random thing, and then there's a payoff. And it's not going to be 0 typically, but on average it should be 0. So we have to do that calculation. What is the average payoff? So what we need to do is we need to say, what's the probability? What is the sample space? Okay, it's a strategy for player 1 and a strategy for player 2. Once they decide on their strategies, once they flip their coins and pick player 1 picks a strategy, say he picks I. And player 2 picks a strategy, say he picks J. Okay, so once you know they pick those two things, then you can look it up in the matrix. Okay? So that given a particular sample, ij, you know what the payoff is. And that payoff is a random variable with value, which we'll denote by x. Okay? So now the expected value, the average cost of this, is just the sum of the probabilities of each one of these entries coming up. Okay? Times the value of those entries. That's just expectation. That's the average value. You just say, what's the probability I get this? How much do I get if I get this? Time plus what's the probability I get this, and how much do I get here? That's the average value. Okay? So now the expectation is, if I know what I can't know anything about what you're choosing. That's the way Rochambeau works, right? Presumably. Okay, so that's the assumption here. And so you want to say you choose independently, so now you can compute the probability of ij. What's the probability of choosing, of getting ij? So what is the probability of that? Well, the probability of choosing any entry in this case, for both the row and the column, of choosing any I is 1/3, and the probability of choosing any j is 1/3. And they're independent, so you can multiply them. So the probability of any ij is 1/9. So if you put in 1/9 and you put it into this formula, you'll get 0. Okay? Right? If you just say, it's essentially just saying add up all the entries in the matrix. If you add them all up, you get 0. Okay? So the expected payoff with these two strategies, and this is very much dependent on these two strategies, since each one plays each option with probability 1/3. Okay? So the expected payoff is 0. Okay. Okay, again, there's only one payoff. This is the payoff both to the column and the row. Okay, so if it's a positive number, the row is happy. If it's a negative number, the column is happy. Okay? So this value is really the row is paid by the column, this value. And if it's negative, that actually means the row is paying the column. That's what zero sum means. Okay. Okay, so now the question is this an equilibrium? So we know intuitively it's an equilibrium, but how do we tell? How do we prove it's an equilibrium? How do we know there's not some other mixed strategies that might be better? Right? There's a lot of mixed strategies. Now we have real numbers here. Right? We used to have we could just look at each row to see whether one of the other strategies was better. But here, these are real numbers, right? These 0.33. So we have to search over all possible mixed strategies and say none of them are better. How could we possibly see that? I mean, it's clear in this case, but why? Why is it clear? Well, the point is, expected payoffs, this averaging has this linear quality. So now the row here, so the expected payoff of rock, say I'm the row player, okay? And I get an expected payoff for a rock. What is expected payoff for rock here? Against the column player playing 1/3, 1/3, 1/3. 0, okay? It's 1/3 times 0 plus 1/3 times 0 plus 1/3 times 1 plus 1/3 times -1. So for each row, if now the player 1 wants to change, but he says, well, any one of my pure strategies is no better. Okay, that we can check. That's easy to check. So there's no better pure strategy. In fact, that means there's no better mixed strategy. Okay? Because against a fixed opponent, you're doing an average over these rows, right? You might as well pick the row that gives you the best value. So if every row gives you the same value, you might as well not pick any other row. Okay? So if I know I'm going to get $100 if I do this and $50 if I do this, what probability distribution should I use? All here, all at the $100, right? I should not pick the $50 at all. So that's what this says. This says, if I just want to do better, I don't want to keep the other person at bay, it doesn't matter. Any one of the strategies is the same. And so this particular strategy I'm using is optimal too, because the value I'm getting from my current strategy is 0. Every pure strategy gives me no better value, so I have no incentive to change. Okay? So that says the mixed strategy is a weighted average of payoffs of pure strategies. So, so this is what weighted average is. So you're trying to optimize this probability distribution. Okay, so you're picking these probabilities, and you're picking over these options, I, J, K, I1, 2, and 3. And this is the value of each one of those options. So whatever the maximum one of these values are is what you should put your probability on. And if none of those values is larger than the payoff you're getting now, you know you're optimal. Okay? So you only need to check pure strategies. Okay? So the mixed strategy can't be better than the best pure strategy. That's what this, I'm just plugging it into the equation. So player 1 has no incentive to change. Because every one of these mixed strategies here has value 0, and his current expected payoff is 0. So it is an optimal point, in some sense, for his payoff. So it's an equilibrium for him. Okay? And it's the same for player 2, right? It's exactly symmetric, this particular game. Okay? So it's an equilibrium. It's one of these Nash equilibriums. Okay, so I think we're done for today. We'll take this up on, after spring break. So enjoy your break.